Compton effect is an effect which proves that the photons or light waves, they are particles. By considering their particle nature, by only then can we explain Compton effect. And in a Compton effect, it's just a scattering of light. It means that when there is a collision of light, how will it behave? That is actually Compton effect. When we say collision means a wave cannot collide, only a particle can collide. So if there is a wave and it's falling on some target, then maybe it will reflect back. So it will reflect back. But if it is a particle, then it might collide and maybe it will behave like a particle. And because this is made up of ions and electrons, any target, let's say if it is any metal target, then you have free electrons and positively charged nucleus. So this material is made up of ions and electrons. So let's say it collides with any electron and it gets scattered in a particular direction, just like any particle would do. So that is why we say that it proves a particle nature of, because this is how a light wave would behave, but scattering is a phenomena of a particle. So this proves that this behavior shows that the light waves, they behave as a particle. Now let's try to understand it further. Before starting with this, I would just like to revise with collisions, just to give you an idea of how collisions work and how the conservation principles work in collision. So let's say, because collision is a behavior of particles or objects, so let's say that you have any mass m1 and it is moving with some speed, and you have another mass which is kept somewhere here, which is m2. Okay, so it moves and it hits this object. So after it hits this object will move in the other direction and this object will move in the other direction. So this is your initial situation where one object is moving and the other is at rest. So this object is at rest and this object is moving. So after the collision, let us say that the first object, which is m1, reaches somewhere here, and the second object, which is m2, it reaches somewhere here. So this now is your final situation. Okay, so this is the initial situation where you have an object moving in one direction and there is another object and it hits this object. And after that, one object moves they both move at a certain angle to each other. Okay, now let us say that they move at different angles. So maybe we can give them different angles. Let us say this is theta and this angle is phi. In a similar manner, let's compare this to a photon electron collision. So if suppose now instead of this mass there is a photon and it is moving in this direction, and there is an electron, and similar situation, photon is moving electron is at rest. They collide just like a particle would collide, and the photon moves away at a certain angle and the electron moves at a certain angle after the collision. So now this is your initial situation and this will be your final situation. Okay. Now all of the calculation depends on this understanding of this phenomena, that they are moving at different angles and how then their momentas and their energy conservation rules will apply. Now these collisions, they are actually elastic collisions. Okay, so whenever there is an elastic collision, there are two things which will be conserved. First of all, energy will be conserved and momentum will be conserved. What is the meaning of conserved? Conserved means that initial energy must be equal to final energy. So initial energy of this object's total energy must be equal to the final, whatever energy they are having now should add up to give the initial energy. And the momentum, initial total momentum, should be equal to the final total momentum. Now, because momentum actually for a particle and a wave is can be given by, now for a particle, momentum for a particle is quite well familiar. It is m into v, whatever is the mass of the particle into the velocity of the particle. It can also be written as, let us say that you multiply it with v and divide by v and also divide by 2 and multiply with 2. So why do I do this? Because if you do this, then momentum of the particle will be equal to, now this half mv square is energy. Okay, so twice of energy divided by v. So it could also be written like this, that momentum of the particle is given by, I hope it is correct, yeah, x. So now let's try to use these equations for momentum conservation and energy conservation. So the initial situation, there is a photon and there is an electron. Photon is moving, electron is at rest. The final situation, photon moves in this direction, electron moves in this direction. Okay, and initially the energy of the photon will be hf and the energy of the electron will be 0 because it is at rest. How about the momentum? Momentum, actually, because they are moving only in the x-axis, so it will be momentum in the x direction. Because they are moving only in the x direction, they are not moving in the y direction. Therefore, we say it is px. Now, in order to find momentum of a wave, first of all, you need to know what is de Broglie wavelength. Okay. De Broglie wavelength connects wave property to particle properties. So, like the wave properties are wavelength, frequency, and so the wave properties are wavelength and frequency, and the particle properties are like it has mass, and it will have momentum also. While if you talk about wave, it should not have momentum because ideally it doesn't have any mass. So de Broglie wavelength can give you wavelength, which will be given lambda is equal to h upon mv. So any wave with a wavelength lambda will have mv amount of momentum. So it can also be written as h upon p, or we can also write as p is equal to h upon lambda. So h upon lambda will give you the momentum of a wave. Okay. So here let's say that the momentum of this wave is p, and because it is at rest it will be 0. Now let's talk about the final situation. Let us say that this angle is theta, this angle is phi. Because energy is a scalar quantity, so we need not think about x and y axis, anything, we can just add it. Okay. While momentum is mass into velocity. Velocity is a vector, so it is a vector quantity, so we cannot add it actually. If we have to find the final and the initial momentum, we'll have to take into account the x and the y components separately, only then can we add them. Okay. So then if suppose it has let's talk about energy first. Photon has an energy of hf dash finally, and electron is also moving, so it will have energy of half mv squared. Okay. And the momentum, so the photon will have, let's say, momentum of p dash, and the electron will have a momentum of pe. So this p dash now can be written in two components, so it will be p dash cosine of theta and p dash sine of theta. Similarly, for electron, if it is pe, so it will be pe cosine of phi and pe sine of phi. So now we have all the momentum values and all the energy values. So now let's use the energy conservation and momentum conservation equations. So let's talk about momentum first. In the x-axis, initial momentum must equal to the final momentum. So in the x-axis, now this momentum initially is in the x-axis. So we'll have the momentum of the photon plus 0 should be equal to, in the x-axis it will be p dash cos theta plus pe cos phi. And in the y-axis, initial momenta will be 0, and in the x-axis it will be y-axis it will be p dash sine theta minus pe sine phi. Okay, so these will be the momentum conservation equations. Let's say this is 1, this is 2. Now how about energy conservation? Total initial energy must be equal to the final energy. So energy of the photon plus energy of the electron must equal to the energy of the photon plus the energy of the electron. Now half mv square could also be written as we did earlier. You can just multiply with m, so it will be mv squared divided by 2. 2, okay, and divide by m and multiply with m. So we can also write it as p square upon 2m, where p is the momentum of the electron, because mv will give you the momentum of the electron. Okay, so then here we can write it as p e square upon 2m. Also, okay, let's keep it this way. So let's say this is one of the equations. Let's say this is equation 3. Now we have these 3 equations, and now we're going to find out. We're just going to solve them to find out what is the wavelength of lambda dash. All this calculation we are just doing to find out this f dash. Okay, because when a photon strikes an electron, it scatters with a different energy, and the total aim of this entire topic is to find out what is this energy, what is this frequency, in a way, because h is known. So we want to know what is this frequency, or we want to know what is this wavelength, because frequency and wavelength, they are related. Okay, so then you have equation 1, 2 and 3. Now let's just play around with these equations. So from 1 and 2, what we can find is Pe cos phi is equal to P minus P dash cosine of theta, and Pe sin phi will be equal to P dash sine of theta. So now we are just going to square and add these two. Square and add. So that will mean Pe square cosine square phi plus sine square phi must be equal to P minus P dash cos theta squared plus P dash sine theta squared. Okay, so we're just taking these two equations and we are squaring them and we are adding them. So then after square and add, what we are getting is Pe squared, this will be equal to 1, will be equal to P squared plus P dash cosine of theta squared minus 2 P dash cos theta plus P dash sine theta squared. So it can also be written as P square plus P dash, because you know it will again be equal to 0, so maybe I'll just write this step for you. So it will again be equal to 1 minus 2 P dash cosine of theta. So we can write it as P square plus P dash square minus 2 P dash cosine of theta. So this will be equal to Pe square. So this is the equation we got from momentum equations. Now let's use equation 3, which is the energy conservation equation, which is HF is equal to HF dash plus Pe square upon 2m. So from energy conservation we know that Pe squared will be equal to HF minus HF dash multiplied with 2m. So this should be equal to Pe squared. So now just let's take this and now let's just equate them. This we have got from equation 3. Okay, energy conservation equation. Now let's equate them. So it will be P squared plus P dash squared minus 2 P dash cosine of theta will be equal to HF minus HF dash into twice of mass 2m. Okay, so So we just let's put the value of momentas, because you know that P is initially, when we said P dash PE, P will be H upon lambda, P dash will be H upon lambda dash, and PE will be actually MV. Okay, but let's keep it PE at present. So now this is the equation we have, and we are going to solve this equation. But so you know that this is for the photon, okay, and this is also for the photon. Okay, so for photon, you know that lambda is equal to H upon mv, so therefore P will be equal to H upon lambda. So then P will be H square upon, okay, before putting the value, let's make some calculation without putting the value. So it will be P square plus P dash square, and what we're going to do is we're going to add minus 2pp dash and plus 2pp dash minus 2 cosine of theta is equal to hf minus hf dash into 2m. So why did we do it? Because we want these terms to be together. So now we can say P minus P dash squared plus 2p P dash 1 minus cosine of theta will be equal to hf minus hf dash into 2m. Okay, now we can put all the values, and what we can say is P should be H upon lambda minus P dash should be H upon lambda dash. If you have forgotten, let's say, okay, so it is P dash and the momentum PE. Okay, so then we can also write for this term, so it will be 2h into h lambda into lambda dash 1 minus cosine of theta. Now let's put the values here. F, let's replace F because F is the frequency, HF and HF dash. So it will be HC upon lambda minus HC upon lambda dash into 2m. So then it turns out to be, let's take H constant, 1 upon lambda minus 1 upon lambda dash plus 2h square lambda lambda dash 1 minus cosine of theta should be equal to HC 1 upon lambda minus 1 upon lambda dash into 2m. Now let's take 1 minus cos theta common, and 1 minus cos theta could be this minus this, so it will be HC 1 upon lambda minus 1 upon lambda dash into 2m minus H 1 upon lambda minus 1 upon lambda dash divided by this term, so it will be 2h square divided by lambda dash. So this is what we have got. Okay, so now what we can do is, let's take h to be common from all these, so it will be h divided by 2h square, this could be taken common, and 2mc. Let's take lambda dash to the numerator, so let's keep it here for some time. then it will be 1 upon lambda minus 1 upon lambda dash minus 1 upon lambda minus 1 upon lambda dash. Okay, so this is what we are getting. Okay, so 1 minus cos theta is equal to 2 mc h upon lambda this minus this. I think we have missed something. I think there should be a square here. So if it is a squared, you'll get a h squared outside. So it is a squared and you'll get a squared here, and you should get a squared here, and then some, and also h should be left because one h should be common and one h should be left with this term. So then now this equation turns out to be let's cancel h with h, and so it will be 1 minus cosine of theta will be equal to 1 upon 2h. Let's take this lambda dash inside here. Let's keep it out first, and then it will be 2mc minus h 1 upon lambda minus 1 upon lambda dash. Okay. No. It will be lambda dash upon 2h and 2mc minus h 1 upon lambda minus 1 upon lambda dash, because it's a square term. So if we take it out, it will leave one of the factors in the brackets. Okay. So now what we can do is, let's take this lambda dash inside the brackets, and what we are going to get is 1 upon 2h. First of all, let's keep it like this. So it will be 2mc minus h lambda dash minus lambda divided by lambda into lambda dash. Also here outside the bracket it could be lambda into lambda dash. So then this term will cancel with this term, and what we are left with is 1 upon 2h 2mc minus h lambda dash minus lambda divided by lambda dash into lambda dash minus lambda. Okay. So let's take this 2mc common, so it will be 2mc divided by 2h, and so it will be 1 minus h upon 2mc lambda dash minus lambda divided by lambda dash into lambda dash minus lambda. So this 2 will cancel with 2, and let's take this term this side, because you know this side we have 1 minus cos theta, so it will be h upon mc 1 minus cosine of theta should be equal to 1 minus, now what we are going to do is, Let's multiply it with C and divide it with C. So it will be hc upon 2mc squared into, let's again bring it back to the same, 1 minus lambda minus 1 upon lambda dash, whole bracket lambda dash minus lambda. Okay. So we can also write it as 1 minus, let's take this hc inside, so it will be 1 minus 1 upon 2mc squared hc upon lambda minus hc upon lambda dash into lambda dash minus lambda. So then this term becomes, now hc upon lambda can be written as 2mc squared. hc upon lambda is hf minus hf dash. Again we are bringing it back to where we started from. Okay. So now this term hf minus hf dash and mc squared. Okay. You know that when we are having a photon and there is an electron, photon goes in this direction, electron goes in this direction. When we talk about energy, then let's say it has an energy of hf, photon has an energy of hf dash, and electron has an energy of this. So if I have to find the energy of the electron, it will be, so hf is equal to hf dash plus energy of the electron. So energy of the electron is equal to hf minus hf dash. And this energy of the electron and this term here, it is also energy because it is mc squared. Okay, so this is also energy because, but here you have the c squared, which is actually very high, and the energy of the electron we are having is mv, mass of the electron into some velocity. So this mv and this mc squared, they are very different. So mv will be very less than mc squared. So that is why this term in the numerator will be very less than the denominator. So it means that hf minus hf dash is very less than 2mc squared. So then if this is the case, then what we can do is, this equation will become where towards the left hand side we have h upon mc 1 minus cosine of theta should be equal to 1 minus something which is very small. So it is a very small number, so let us neglect it. Okay, and lambda dash minus lambda, so it will be a very small number, so we neglect it, and what we are left with is h upon mc 1 minus cosine of theta should be equal to lambda dash minus lambda. So lambda dash will be equal to lambda plus h upon mc 1 minus cosine theta. So this entire exercise was just to find out this lambda dash, this energy, the frequency f dash. So now this lambda dash will be greater than lambda by this factor. So it means that if there is a photon coming with some energy, some wavelength, when it will be scattered, the wavelength will be more. So this wavelength will be lambda dash, and this wavelength will be lambda and electron. So it will be larger wavelength as compared to a wavelength which is of the incident photon, which is moving in this direction, this is moving in this direction. Okay, so this is it about the Compton effect.